All right, welcome everybody. Good afternoon. My name is Jacinto de la Cruz Hernandez. I'm a research and reporting analyst for the TAMIU ARC grant here that is aimed at helping our graduate students. And we hold these professional development workshops for the community, for the TAMIU community. And today we're going to be looking at an introduction to machine learning in Python. It's going to be a pretty broad introduction. We're just going to go over a lot of the concepts and ideas of machine learning, but we will take a look at some specific examples of how to apply some of those methods in Python. But you don't need to have any Python experience to benefit from this workshop. The idea here is for you to get some exposure to the ideas and the methods of machine learning to try to get you on your way. It's too broad, too deep of a concept to cover in a lot of depth in just this short time. So we'll just kind of go over some broad ideas, see a couple specific examples, and try to get you just exposed to these concepts. So let's get started. The way we're going to look at this today, we're going to start off just by talking about the objectives I have for today, the goals and what I want for you to leave from this workshop with. We'll talk about machine learning a little broadly, some of the different methods and the different ideas in machine learning. We'll talk about Python, right? Why we use Python for machine learning and how we use it. And then we'll go into depth into some of the different methods in machine learning that we'll be taking a look at using Python. So first off, this are my expectations for today's workshop. So I want you guys to leave here with a better understanding of what machine learning is and what it can be used for. Hopefully you'll be able to recognize the difference between the different types of machine learning techniques that fall into supervised learning and unsupervised learning. You'll gain some exposure to the free resources that are available for you to apply these machine learning models through Python. And hopefully you'll be able to pick the correct machine learning method to use for a particular task. So let's get started on machine learning. So what machine learning is it's really a subfield of artificial intelligence. People think about artificial intelligence as, kind of like androids, really futuristic stuff. But really, machine learning falls into artificial intelligence because we are programming computer systems to really learn from data and to perform tasks without being explicitly programmed to do so. So in a regular computer program, you have to encode all the steps that you want the program to follow to perform a specific task. Whereas with machine learning, you kind of start off with a broad structure that you feed a lot of data into. And at the end, the program should be able to perform a task that you didn't really specifically program it to do, right? It should be able to learn from the data on its own. So an example of this would be an image classifier where you can feed it pictures and it should be able to tell you, is this a picture of a dog or is it a picture of a cat? Right? You don't have to tell it what to look for in the picture. You just have to give it the data, give it a bunch of pictures, tell it this is a dog, this is a cat, and it should be able to recognize those things on its own. It'll pick what are the important features in those pictures to determine whether something is a dog or a cat. And machine learning is really widespread in pretty much any industry, right? So all the recommendation systems from YouTube to Netflix, they're all working on machine learning. The machine vision that's used for, let's say, self-driving cars or facial recognition systems, those operate through machine learning. And in the medical field, diagnosis tools can be developed using machine learning as well. So broadly speaking, machine learning tends to fall between these two separate types of learning. So we have supervised learning, where you're giving the machine learning algorithm labeled data, and it learns to associate the input features with the corresponding output labels. Right, so examples of this boil down to regression or classifier algorithms, and we'll go a little bit into detail on those in a moment, but the idea is we're giving the algorithm labeled data, right? So we give it some input with the correct answer, and it learns how to go from the input to the output, right? In unsupervised learning, we give the algorithm unlabeled data. So you can just give it anything without a specific right answer, right? There's no thing that you're giving it that you are expecting it to give you back based on the input data, right? You're just giving it unlabeled data. And basically the machine learning algorithm will try to learn something from that data, right? So ways that we can use this are in clustering and dimension reduction. And we'll go into a little bit more detail about that later. But again, so here the big distinction is when we are using supervised learning, we are telling the algorithm what we want, right, out of its process, right, what we want as an output, versus in unsupervised learning, we're pretty much letting it work on its own and give us something for us, basically, for the algorithm to discover something in the data that you give it. So why Python? Why are we going to use Python for machine learning? Well, Python is already one of the most widely used programming languages for machine learning, and there's a few reasons for this. It's fairly straightforward and high level as a programming language. That means unlike maybe something like C++, you don't have to get too into the weeds of how the program is really controlling the systems in your computer, right? It's pretty high level, it's pretty surface level, and it reads somewhat like normal text, right? It's often considered a pretty easy to learn language. There's also already a large list of available libraries for Python. So there's already a lot of resources out there for you to use of basically pre-coded data and programs that you can use through Python. Python is also used in pretty much any field, and most of all, Python is free. So it's easy for you to access, and because it's free, it also means since it's easy for people to access, there's a lot of people working with it and making things that you can use in your own projects. So we talked about the libraries, right? What are Python libraries? So these are going to be collections of pre-written code or modules that provide usable functions and tools that will simplify your experience developing software and programs through Python. Right, so that means there's collections of code that has already been written so that you don't have to code everything from the ground up. Right? You can use other people's functions in order to make your job a lot easier. Some of these libraries and the ones that we are mainly going to be using today and that are really commonly used in machine learning are going to be NumPy, which is a library that allows you to create and manipulate numerical arrays. So you can think of these as mathematical vectors and matrices, which is going to be very important for machine learning. There's libraries like pandas, which allow for data manipulation. You can load data, write data, and manipulate your data using pandas. Matplotlib is a library that allows you to plot figures using Python. And the main meat of this workshop is going to be the scikit-learn library, which has a lot of already built machine learning tools that you can use. So you don't have to code these machine learning algorithms from the ground up. You can use the functions that are already given to you through scikit-learn. And you just have to learn how to apply those, essentially. So Today we're going to be working with Python through the Jupyter Lab environment. So this is going to be an IDE for Python that is free. It's available online. There's a version that you can download and use on your own system. But for ease of access today, we're going to use the online version of it. And with this system, you can write what are called notebooks, which let you write and run Python code through this Jupyter environment. And there's a link here for you to access that. So let's open that together right now. So when you open up the link to Jupyter Lab, you should be taken to a screen like this, where you have a list of files here on the left, and you have the option to create new notebooks, right? This Python iodide notebook section is what you're going to use when you want to create a new Python notebook. But in this case, you should have received an email with a Python notebook attached to it, which is how we're going to use the code for today's workshop. So let me get back to the presentation here. So to get started, we are going to open up Jupyter like we did there. And we are going to download the notebook provided for the workshop. So if you received the email, you can download it from the email that you received. If not, you can scan this QR code, or you can follow this link, which we'll do together right now, to open up. Okay, perfect. Thank you. So the links will be available in the meeting chat if you didn't get these. So open that up. So when you open up the link to download the file, you should be taken to this Google Drive link. You can download the file, and the file will be in your downloads. So with that downloaded file, we're going to go to Jupyter, and we're going to click on this arrow up here on the top left corner. And the instructions for this are also in the presentation, so you can take a look at that. So we'll go to that arrow in the top left corner that lets us upload a file. And we're going to look for the file, so it should be in your downloads, and upload it. Once you upload it, the file should appear on the file list here in the Jupyter Lab. And you can just double click it to open the file. And here we have the notebook that we'll be using to run all the code for today's workshop. So let me get back to the presentation here. Just here are the instructions, right? So again, once you're open on that Jupyter Lab page, you go to the arrow up here on the top left. You upload the notebook file that was provided to you, or that you can download through the link here. Right? And then you just double click on the file once it's uploaded to open it. Okay. So before we get to the actual code, let's talk a little bit about the things that we're going to be looking at. All right. So first off, we're going to start with supervised learning. So we talked about supervised versus unsupervised learning. Supervised learning, again, is when we're going to feed labeled data into our machine learning algorithms, where we give the system a set of inputs and the set of outputs that we want to get from the algorithm. Right? The algorithm takes these inputs and outputs and learns how to go from the inputs to the outputs. How it does it depends on the kind of algorithm that you use. But the idea for supervised learning is we're giving it labeled data with inputs and correct outputs, right? So a couple of methods that fall under supervised learning are going to be regression and classification. You should be somewhat, if you have any sort of mathematical training already, then you would be familiar with some of this. If not, basically regression is going to be predicting continuous outputs, right? So you're feeding the algorithm some inputs, and it should give you a continuous output, right? So that means some number. It could be a decimal, it could be a whole number, any number, any real number essentially is going to be your output. In classification, we are feeding the system inputs and we get out either a category or a class. Basically, these are going to be discrete outputs, right? We can only get a certain number of outputs, right? There's only a specified set of outputs that we can get. It's not like a continuous output where you have any number is available. With classification, we only get one of a set of possible outputs. And these kinds of models are used in things such as credit risk assessment. So when banks are determining whether somebody is likely to default on their loan, right? That's a binary output, right? They either default or they don't. So that would be a classification problem, right? Or if they're trying to diagnose a disease, again, do they have the disease or not? That could be a classification problem as well. Image recognition, again, if you're trying to determine whether a dog or a cat is in a picture, then that's a categorical outcome. And spam email detection as well, if your email is spam or not, again, classification. So what we're gonna do is take a look at the notebook. We're gonna switch over to the notebook and we're gonna take a look at some, sorry about that. We're going to take a look at some of our supervised learning examples, right? So a quick word here, I just want to say thank you to the Sweeter team from Texas A&M University. A lot of these examples I got from a workshop that I attended at their Sweeter Winter Computing Festival last December. So here's just a brief overview, again, of some of the same things that we already talked about, classification, regression, and these are some other methods that we'll also take a look at today. Let's take a look at our supervised learning methods. So we're going to start off with regression. So if you have any mathematical training or statistics training, linear regression is going to be one of the basic statistical methods that you're going to learn at the very beginning of your training. So linear regression is actually something that falls under machine learning because we're giving a system a list of inputs and outputs, and we're expecting the system to give us a particular output, in this case, a continuous variable, based on the input variable, right? So what we're going to look at today is, for a lot of these examples, we're going to be generating a data set like we do here. So you can use Python to create your own data sets. There's some libraries that also offer just data sets built in. And we're going to transition between those two for these examples. With this first example, it's going to be a very basic linear regression with one input and one output, right? So in linear regression, our input tends to be our X variable, and our output is our Y variable. Now, I said, if you don't have any Python experience already, a lot of this is probably going to look like gibberish to you. So don't worry too much about the code. Try to follow what I'm talking about and try to understand the concepts. If you have experience with any other programming language, maybe it won't be too hard for you to try to follow the code here. But if you're cracking your head and you can't get it, don't worry too much about it. Try to focus on the concepts, and I'll guide you through the code as we go along. Okay, so I left all of these comments. As you can see, everything after the hashtag is going to be a comment in Python. So basically, the program is ignoring all of that text. All of those are just comments for you to read. So when you go back to this later on, you can try to understand the code a little better if you can't keep up as we go along. So like I said, first we're generating a data set. We're generating a data set with 25 entries. This NumPy function right here gives us a vector that goes with entries that go from -1.5 to 2 with n sample entries, right? So that means we have 25 entries in this vector. right? So this is essentially a vector with 25 entries going from, we can see in our graph, negative 1.5 to 2. And then we make y values based on those x values. You can see here we have a linear relationship. We have 3x plus 2, and then we're adding a random term, right? So that's how we get that kind of random behavior on our line. We want some randomness there so that our program has a little bit of trouble figuring out the original function, right? We don't want it to just have an easy, here's a perfect line, right? So we're trying to simulate somewhat what real data would look like. Then we can just plot those x and y values here, and it gives us this graph. So this is the original data that we're going to be working with here. We can check the dimensions of our x and y vectors. So you can see x and y are both vectors with 25 entries, and they're column vectors, so they have one column. So these are rows and columns. If you're going to be working with machine learning, linear algebra is going to be huge. So if you ever have trouble with linear algebra, I recommend that you go back and review, because that's going to be a really big part of machine learning if you want to understand these concepts a little bit more deeply. But right now, we'll try to just go over this as generally as we can, right? So the idea here, right, again, we have 25 inputs and 25 outputs. So we're going to be defining our model as a linear regression model, right? So something I forgot to mention up here, when using Python, if you haven't used it before, you see at the beginning, we're going to import all the libraries, right? So matplotlib, numpy, and sklearn are our libraries. And we're importing certain functions from those libraries. So linear regression here is a function from the sklearn library. So we are defining our model as a linear regression model, and we're going to fit it with our data. And that means we're going to feed the data that we've generated into this model so that it can fit a line, right, a linear regression to that data. We can ask for the model's coefficient once it's trained, which is this, 3.1377, so on. And we also get an intercept, right? Those are the two things we need for a line. And we can ask the model to give us a score, right? So if you've done linear regression before, you know we use the R-squared coefficient to determine how well the line fits to the data. Right? And we can visualize that as well by plotting the linear regression line and the data. So what we're doing here, right, again, we're plotting the original data. All those points are the data that we generated, right? They're along the line plus some randomness to it. And our model decided that this line here is the line that fits it the best. Now we can see that this line is actually pretty close. The original line is just 3x plus 2. So this is pretty close to that original line. And we can quantify that with our R-squared coefficient, right, where 1 would be a perfect correlation. Okay, so this is a simple example of the linear regression model that you can use through, right, the sklearn library. Right? So let's try applying that model to some data that's a little bit more complex, something that you're more likely to see in the real world. So like I was saying, some libraries include data sets, right? So the sklearn library here includes some data sets that you can download to use for your own machine learning models. So here we're going to import the data sets from sklearn, and we're going to import pandas, right, which is a library that I said would allow us to load, save, write data, manipulate data, and so on. So we're going to load the diabetes data set that is available through sklearn. And what that data set gives us is we have some input variables. So we have all of these 10 variables that are correlated to some output variable. So this, the target is our output. And what these are some measurements that are being used to determine a person's progression through diabetes. So we can see our target here is continuous, right? We have just real numbers as our outputs. So because our outputs are continuous, we're going to use regression. In this case, we're going to use linear regression. And what we're doing, right, is getting all of these 10 outputs and trying to generate, 10 inputs, right, and try to generate these outputs in the target variable. Right. So we're using pandas here to make our x, which is our input variables, and our y, which is our output variables, right? We're separating that into the inputs and the outputs. So what I did here was just graph those outputs, right? So here we can see for each of the observations, we have some output along this range, right? We have continuous values. They can go anywhere. And so these are the things that we're trying to estimate with our linear regression model. So just like we did in the simple example, we have our linear regression model. We're going to fit it to the X and Y data that we just generated. We're going to score the model, right? We can see here it's not doing as good as it did with our fake data, right? Which is to be expected. Real world data tends to be a lot more complicated. So when we score that model, we only get about a 0.5 R-squared coefficient, which isn't great. And then we can predict what the model thinks the outcome is going to be for the data that we have. All right, so let's review the steps here, right? We fitted the model. We gave the model the input and the output variables, right? This is a supervised learning method. So we're giving it inputs and the correct outputs that we expect, right? The model will do its best to approximate those outputs. And then once the model is trained, we can use that model to predict what the outputs for certain inputs will be, right? So in this case, we're again feeding it the inputs, X, and asking it to predict what the outputs for those inputs will be, right? So we're saving that as this new variable Y fit, right? So these are the predicted outputs. And so down here, I'm just plotting all of these original inputs, the predicted, not original inputs, original outputs, and the predicted outputs, right? And I'm plotting them against each other, and we can see the red is a predicted, and the blue is the original. So we can see sometimes it gets them pretty well, but it seems like it has a lot of trouble with the really extreme values, right? With some of the extreme values, this model isn't catching them very well, right? But it's doing somewhat good with some of the more mid-range values, right? So how well the models do is going to depend a lot on the data that you feed it. In this case, it just looks like this data is not going to be, it's not going to work very well with our linear regression, right? But this is only one of the kinds of methods that you can use to apply regression to some data, right? So for each of these examples, I have a little bit of an exercise that I'm going to give you maybe, let's say, just 2 minutes to take a look at and go back into the code and try out. Again, if you don't have any Python experience, maybe just think about the question, what do you expect to happen? So in this case, I'm saying, what would happen if I drop the BMI variable from our predictive variables in this example, right? In this diabetes example. Let's say in our variables up here, BMI, I'm going to get rid of. I'm just going to use the rest of the variables. What could we possibly expect from our model, right? So let me just go back to the beginning here and start running all of these codes. I run all of these lines of code, okay? So I'll give it a second to compile. So right now we're just seeing all the results from me running the code originally, but so now I'm running the code again, and so we can see now that I reran it, we get a little bit different on our random data up here for the first linear regression example. And so our regression line is a little bit different, but again, it's still in that ballpark of 3x plus 2, and the score is still pretty high, right? So now, okay, so all of this is done. So again, with the diabetes example, our score isn't very good. So if you have some experience with Python and maybe you already tried dropping the variable and rerunning this code, let's take a look at what happens, right? So I'm gonna go back here to where I defined x. So for x, I defined it as our original data, right? Our data up here without the target variable, right? That's our output. So we don't want that in our inputs. So what I'm just gonna do here is to that list, I'm gonna add BMI, right? So if I add BMI there and I rerun this section of code, you see, now I only have 9 input variables and BMI is no longer in there. So I got rid of BMI from my input variables. So I'm gonna rerun everything else. Again, the output variables are the same. I fit the model here, and then I get a score, and look at that, our score went down, right? So it looks like the BMI variable was doing some work, right? If you thought about the question, maybe that's what you expected, right? If you take out one of the variables, maybe the model is going to perform a little bit worse, right? And it did. And it's hard to tell from the visual if it's better or worse, but we can see from the score, it did go down, right? And the visual doesn't look much different, right? We're, again, not capturing a lot of those extreme values. So that would be our first example for linear regression. Whenever you're trying to predict a continuous output, linear regression is one of the methods that you have available. So how about classification, right? So you're trying to determine, based on some inputs, whether your data points belong to one class or another, right? To one category or another. The first model that we're going to look at is called a support vector machine. Right? So what this is going to do is it's going to look at your data, and it's basically going to try to draw a line separating the classes of your data, right? So again, for this example, we are generating data, right? So this is fake data. We're just generating it with some random functions, right? So here we're making 2 sets of blobs. Right? We're asking for 2 centers, and we're giving it a standard deviation of 1, right? So that they're kind of spread out. So this is what we get as a result from that line there, right? So we get these 2 blobs of data, right? We can see there's a little bit of overlap, but not too much, right? So our support vector machine is going to try to find what's the best line that can separate these 2 sets, right? So let me run this real quick. So again, we're going to import a function from sklearn. This SVC is a support vector machine classifier, right? That's what the C stands for. And the support vector machine has a couple of different kernels that it can use. So it can use lines. It can use different types of lines to separate our data. It could use straight lines or curved lines, depending on what kernel we give it. For ease of visualization here, we're going to use a linear, which is a straight line. But right now, I'll show you what some of the other examples may look like with a different kernel. So here we're asking the support vector machine to look at our data, right? We're going to fit it with our inputs and outputs. And we want it to give us a straight line to separate our data, right? And you can see in this plot that it does that, right? And it does it pretty well. Again, there's some overlap in our data. So there's some, yellow points in the blue section and some blue points in the yellow section. But overall, it's pretty good. It's a pretty good separation. So essentially, with this model, you would see everything that falls on top of this line is going to be a blue point. Everything that falls under it is a yellow point. Right? So if you're trying to classify something with two possible outcomes, right? A binary classification, you could use a support vector machine like this. And if you have, so this would be your training data, right? And if you want to use it for some new data, right? You trained your model. This is what the model is going to do. And let's say now I have new data and I want to apply my model. Now you know if the coordinates of your new point are somewhere above this line, it's a blue point. If they fall under this line, it should be a yellow point, right? So this section here is going to be really in depth. So if you're new to Python or machine learning, don't worry too much about this section. This is a little bit more complicated. But I wanted to show you what it looks like when your support vector machine has different kernels, right? So again, here we're using the linear kernel, and it gives us a straight line separating our data. But what if we wanted to have a curved line? I can give it the polynomial kernel, which is just giving it a command of poly. Oh, I didn't run this part. See, so now we can see our data is being separated with a curved line, right? So in the linear model, a point that would fall maybe somewhere over here may have been classified as yellow before, but now it will be blue because our line curves downward down here, right? So it could be that polynomial line will be a little bit more accurate to the data that you have. It could be that it doesn't work out for your particular data. It's a matter of seeing what works for the data that you have, right? These models are very dependent on the data that you feed them, as we saw with the diabetes example, right? And there's a couple other options that you have here. There's RBF. See, and what this does is it encloses one of your classes, and everything outside this area is going to be classified as yellow. Everything inside the area is classified as blue. And then we have the sigmoid kernel, which we can see for this data works terribly, right? If we try to use the sigmoid for this data, we can see a lot of our blue points are in the yellow region, and a lot of our yellow points are in the blue region, right? So again, it's a matter of what fits best for your data. And in this case, the linear would probably be the best one. We did generate this data, so it's pretty simple. So we don't need anything too complicated to classify these data points. Okay. If I go too fast at any point, or anybody wants me to go back to anything, please feel free to leave a comment in the chat. Again, this is a very general overview of machine learning. I just want to expose you to some of the methods that are available. I want you to find out about what kind of resources are available if you want to apply these methods, right? So there's Python. You can use Python through this Jupyter Lab environment, and there's all these libraries that have functions ready for you to use, right? So if anybody has any questions at all, please stop me. I don't want to focus too much on the code because if you're not experienced with Python, I still want you to get some knowledge about what these machine learning models are, how you can apply them, what are the names, how you can learn more about them, right? So let's take a look at another classifier. All right, so in the previous example, we had binary data, right? We had two possible outcomes. Now we're going to use this KNN classifier to classify just categorical data. In this case, we're going to give 4 possible outcomes. So again, we're generating a data set just like we did before, but instead of 2 centers, we're making 4 centers for our blobs here. So this is the data that we generated. We have 4 different groups of blobs with different colors to designate what group they belong to. And there's a little bit of overlap between the groups, but they're generally pretty well separated. And so what this KNN classifier is, it's the K nearest neighbors. It's going to look at all the data points. Well, it's going to look at K data points near each point, right? So let's say we're looking at this yellow point that's out here on its own. What this model is going to do is it's going to look at K points. We're going to define the K. So let's say we use 4 points. So it's going to look at the 4 points that are closest to this little yellow point. And based on the color of those points, it's going to color this point, right? So in this example, let's say if it's looking at this yellow, it's probably going to look at these 4 points over here, all right? Maybe this blue one over here is a little bit close, but I'm sure these 4 are probably closer to that, all right? So it's going to look at those 4 points and say, well, these 4 are yellow, and they're the closest to this point, so this should also be a yellow point, right? And that's how this model is going to select what class a point belongs to, right? So let's create the model. So we're saying this KNN is going to be a nearest neighbors model, a classifier. And we're giving it here, we want to use 4 points, right? So we're saying when it looks at a point, it's going to look at the 4 points closest to that point. And this uniform weights just means that it's going to value each of those points equally. It doesn't matter how far they are. If they're the 4 closest points, they're all going to be treated equally to classify that point, right? And then again, you just fit that model to the data that we generated. We're using still supervised learning, so we're giving it inputs and we're giving it the outputs that we want. Again, supervised learning, we give it labeled data with inputs and the correct outputs. So what we can do here is let's make a new point, right? We trained the model. Now let's make a new point and see how the model does, right? So I made this new point. I just chose the coordinates 2 and 7. And I asked the model here, predict the class for that point, right? This is a classifier model. So I want it to give me what class that point belongs to. And I'm saving that as R, right? Here, when I print R, right, it gives me 0, right? It's labeling these classes as 0, 1, 2, and 3. So this one is telling me it belongs to class 0. So when I plot it and I use the same colors that I used for my original data set, I can see these are all my original points. This star here is my new point. So when the system looks at the 4 points closest to the star, which if we look at it, maybe it would be like these 2 green ones, maybe this yellow one, and I don't know, maybe one of these green ones, right? It's going to say, well, 3 of these are green, so it made my new point green, right? And so that's how you would apply this model, right? Once you give it the variables, right, the features that you use to train the model, you give it those features for a new point, it will take those features and compare it to the other points that are closest to that point, to that new point, right? So for these classifier models, right, let's try switching the coordinates for this new point that we have here, right? So try, I'll give you 2 minutes, try it on your own up here. You can just delete these and give it new coordinates, right? And then just rerun that box. You can press Control Enter to run it, or you can just press the play button up here and just give it 2 new coordinates and run it, right? I'll give you 2 minutes to try to do that and see what happens, right? And you can try it again, try multiple times. See, try to see where those points are going to be classified based on their coordinates. And if you have any questions, feel free to type it in the chat. Okay, so let's take a look at a couple examples here. So let's try, let's say, let's keep it at that height, but maybe let's move it closer to the center, right? Let's say maybe the x coordinate goes down to 1.5, and we keep it at the same height, so 7. What happened here? Oh, I didn't run this one. Yes, right. So when I run that again, you see my star is now a little bit further to the left. And now look at that, it's closer to more yellow points. So the star is now yellow, right? And the class that it belongs to is class 3. So that's telling me class 0 is the green points, class 3 is the yellow points, and the blue and purple are gonna be, 1 and 2. And you can try this with whatever numbers you want, right? We could go way left. Maybe let's try -2. Oops, that's -2. And well, now the star is a little bit hard to see. It's kind of hidden behind these yellow points, but it's straight there in the yellow area. So of course it's yellow. And if we bring it down a bit, let's say to 5. Now it turns purple, right? It's down here in the purple section, right? So again, this classifier model, here we're using 2-dimensional data, right? Because in order to visualize it, we're not going to be able to visualize something with a lot of dimensions, but you can apply this to however many variables you have, right? So like we did with the logistic regression, right? Over here, we started our example with a simple example with 1 variable, but then we applied that same model, right? The process was the exact same thing. We just defined our input and output data and fed it to the model, right? And it gave us some results, right? The same applies to this KNN classifier, right? If you have data with more than 2 variables, that's fine. You're not going to be able to graph this neatly in a 2D graph, right? But you'll still be able to get a result, right? You can get a numerical result. You can look at the class that your data is being classified as, right? So those are a couple examples of supervised learning. Again, to train these models, we gave the system labeled data with inputs and the outputs that we expect from that system, right? All right, so I'm going to try to go through this a little bit faster because we're running out of time really fast here. But again, so now we're going to take a look at unsupervised learning, right? Again, I just want to expose you guys to some of these methods and give you some resources that you can use if you want to continue learning about machine learning, right? So clustering. This is usually what's used for things like recommendation systems. This is unsupervised learning. That means we're going to give this system data with no outputs, right? Just input data with no labels, and we want to see what this system learns about the data. All right. So again, we are making our own data here. We're using the blobs. We're making blobs with 4 centers. Again, so 4 clusters of blobs. This is the data that we generated. When we use this k-means model, right? So up here, we're defining our machine learning model. We're using the k-means. This is very close to the k-nearest neighbors model. Look at this, right? We're fitting here just x values. We have x and y values, but this model is just taking in the x values. And what it did was we asked it, give me 4 clusters for this data, right? So it gave me 4 centers. And when I graph these, I'm graphing the outputs here. I'm getting the predictions for my inputs. And these are my predicted outputs. And when I do that, you can see this is how the system decided to cluster my data, right? So I gave it this is the original data. It was separated into these 4 groups with a little bit of overlap, but they're pretty separate. And I just gave it the coordinates. I just gave the system those coordinates and told it, separate this data into 4 groups. And it did a pretty good job at replicating the original data, right? We can see some of the points, maybe this purple point up here is now, I don't know if that's gray or blue or whatever. Have a hard time with colors sometimes. But we can see some of these points changed colors, but overall, it grouped the data very close to what the original intent was. Now, sometimes we don't know how many clusters our data is separated into, right? So for this exercise, right, what I want you to think about is, if I change the number of clusters that I ask for from the model, you know, how is that going to change how it clusters the data, right? How's that going to change the groups that it separates the clusters into, right? So we know there's originally 4 actual groups in this data, but what we're going to do is give the model, ask the model for just 3 groups, right? And I'm going to rerun all of this. If I ask for just 3 groups, look at that. Now the model is saying all of this stuff in the middle is 1 group. These 2 groups at the top and at the bottom stayed pretty close to the original data. The model doesn't know that these belong to 4 original groups. We just told it, I want you to separate this into 3 groups for me. So if, let's say, I didn't know what the original grouping is for this data, here what this is telling me is, well, it looks like these things in the middle are pretty closely related, right? Notice the model chose to put all of this stuff together instead of maybe putting stuff from the top with the left or putting stuff from the top with the middle right? It chose all this stuff in the middle is the closest to each other. And these 2 groups at the top and at the bottom are pretty different. So it kept those separate, right? So we could say, if we don't know anything about this, you know, maybe we could say, well, these 2 groups in the middle, maybe those are pretty closely related, right? They're more closely related to each other than they are to the other 2 groups, right? So these kinds of methods are great for discovering things in your data, right? You don't already know what's going on in your data. You're just trying to see, what does this system think about your data, right? So that's clustering. Another application of unsupervised learning is going to be dimensionality reduction. And now this is technically usually something that you are going to use as a process of a bigger project. Usually dimensionality reduction is part of a bigger goal. Dimensionality reduction means that we're taking a large number of variables and basically trying to squish it down into a smaller number of variables. In some applications, you can think about this as, you know, if we have 4-dimensional data, we want to bring it down to 2 dimensions so that we can visualize it, right? So I'm going to skip over this whole first section. This is just looking at the data that we're working with. Right? This is actually a real-world data set that you can get through sklearn. Again, it's part of the sklearn data sets. And these are iris flowers, and it includes the length and the width of the sepals of the flower and length and width of the petals of the flower. And we categorize the flower into 3 distinct species of iris flowers based on those features, right? So we have 4 features. So let me go up here, right? So this is just a piece of our data, right? We have 4 features: sepal length and width and petal length and width. And we have our output, right? Which is a category of iris flower that they belong in. So for dimensionality reduction, right, what we're doing is we're going to take those 4 features and squish them down into less features, right? So in this case, here I can't graph all 4 features at once, right? So here I'm graphing 2 features versus each other, right? So sepal width versus length. We can see the Setosa species of iris is pretty unique. It doesn't overlap with the other species, but there's some overlap here between the versicolor and virginica. When we look at petal length and petal width, we can see, again, the Setosa is completely isolated on its own, so it's pretty different from the other 2 species. And here, there's a pretty good separation between the other 2. There's a little bit of overlap, but not as much as there is on the sepal length. So this is all information that we have across 4 variables for this data. What we want to do, what we're going to do here, let's see, did I run all of this? I'm going to run. Okay. So what I'm going to do here, taking a look, we have 150 data points with 4 variables. We want to squish that down into 2 variables, right? So we're going to use this method, principal component analysis, which basically gives you 2 components. In this case, we're asking for 2, right? It's going to give me 2 components that encapsulate the information that is captured by the 4 variables that we have, right? So what this is going to do, we're going to train this model on our input data. Again, notice we're just giving it input data. We don't care about the outputs. The model doesn't need to know the outputs. We're just giving it input data, and we're asking it to give us 2 components. When I do that, I can take a look at my data set, and it is now 150 rows. So again, the same data points, but only 2 columns, right? Only 2 variables. And when I graph my data across those 2 variables, PC1 here is my first principal component, PC2 is the second component, and we can see there's a pretty good separation between all 3 species of flower across these 2 components, right? So what we had in information across 4 variables, we're displaying over just 2. So now we only need this 1 graph instead of these 2 graphs. And we can take a look at the explained variance of our model. What this means, you can think of this as the amount of information that's captured in each component. So what this is saying is this first principal component is capturing almost 93% of the information in those 4 variables. The second component is capturing another about 5%. And if you want to know, these are the 2 components. Right? They're linear combinations of our original 4 variables. So it's 0.36 of the sepal length, negative 0.085 of the sepal width, and so on. Right? Those are the 2 components that we're breaking this data down into. And they're capturing almost everything in our data. And you can try out that exercise on your own later if you want to take a look at that. Basically, just switch the components here from 2 to 3 and see what happens. See if anything changes. So I'm sorry I had to rush through a little bit of the rest of this stuff on unsupervised learning. And I wanted to do a little bit of a pop quiz, see what you guys thought about these scenarios. And that wasn't supposed to come out at the beginning, right? So you can take a look at those on your own, see if you can guess what the right answers are for those cases. What machine learning method would you use in these cases? But beyond that, I would also like for you to check out these additional resources. So there's, like I said, there's a lot more into machine learning. It's a really deep field. What I covered today is not even scratching the surface. I would really recommend, if you're going to go into this field and you really want to learn about this, you're really going to need a lot of statistics and linear algebra, because everything we did today under the surface, under all those functions, it's all linear algebra that's operating there. It's a bunch of vectors and matrices. So I would recommend reviewing that stuff if you really want to go deeper into this. And if you want some more Python resources, Anaconda is a great just one-stop shop for a lot of Python resources. Kaggle is a website where you can find data and code that's uploaded by other data scientists all over the world. You find made-up data sets, you find real-world data sets. I think there's things like Tesla has uploaded data up there. You can find a lot of stuff to practice and hone your skills in Kaggle. And this Data-Driven Science and Engineering is a book that I learned with when I was learning about machine learning and just data science overall. It's a fantastic book, and the authors of the book have free lectures on YouTube that you can access that go through all of these methods in detail. So that's another great resource, and the website for the book even has code that you can download and try out yourself. So I'm sorry that we don't have enough time to go a lot deeper into this. It's an iceberg of things under the surface here for machine learning. But I hope you could at least get some of these learning objectives that we talked about. And I hope you have a better understanding of what machine learning is. Oh, what happened? Ooh. So I hope you have a better understanding of what machine learning is, what it can be used for. I hope you know the difference between unsupervised and supervised learning a little better. You got exposed to some resources available for you for free that you can use to start applying these models and learn more about them. And hopefully, if you look at those scenarios at the end of the presentation, you can pick the right machine learning method that you would have to use for those tasks. So thank you all for being here. I hope this was helpful for you. I hope you learned something new. And if you have any questions, please feel free to put it in the chat. I can reach out to you if there's anything that I can't talk about at this moment. But I'll be glad to answer any lingering doubts, or if you want me to go back and take a look at anything really quick, we can go over that too. Thank you all so much for being here.